All right, welcome back. Welcome back. So thank you very much for finishing up the survey for topics that you want me to cover. So based on the survey, I find out most people are more confused conceptually when we're talking about, say, entropy, and also when we're talking about the heat capacities, enthalpy, and also Joule-Thomson experiment, etc. So in today's lecture, I'll go over a lot of true and false problem with you. So the goal here is not to say get the answer, whether it's true or false. So while we're working through the true and false problem, I want you to pay attention and just think about it. Now, I told you this is wrong, right? How can we make this statement true? Or the statement is true by removing which condition the statement will become a false statement. So don't spend too much time trying to write down everything I said. Again, I posted a detailed walkthrough with bullet point of each true and false problem on our Brilliant site. So you will be able to access those later on. So in the class, let's just make this a discussion, right? Think about each problem, whether or not it's true, why it is true, whether or not it's false, how can we make it true? So on top of that true and false problem, I also have one sample problem, which is on kernel cycle. So that's also highly voted to be confusing, like heat engine and kernel cycle, and also efficiency, etc. So in this example, I'm going to give you a different cycle. So it's not a kind of kernel cycle, but using the material we learned, we can calculate the efficiency of a different cycle, given that we know how each processes are taking place. All right, so two goals, true and false, and then one application of efficiency in this case. So these true and false problems will, either they just show up as true and false, or we can easily change it into a short answer problem. So maybe ask you to explain why this one is true or false, right? So, and the second example we did is more like a comprehensive problem with multiple parts. All right. Before we get started, do we have any questions on administratively or anything? Okay, and people in the back can see these characters. They're a little bit small. Okay, sounds good. Let's get started. So this question has all the way from A to V. So I'll just go it one by one. Hopefully we'll spend about 1 minute for each question. So let's read this together. First question, is delta H a state function? So raise your hand if you think it's true. Raise your hand if you think it's false. Right, so it's like half and half. So this is one of the tricky questions. When answering it, you want to write down what you know about the question. So in this case, I'm going to give you two more pieces of information. First of all, we know that delta H equals to H final minus H initial, or H2 minus H1. Secondly, in chapter 1, we say what is the definition of a state function. The full description states a thermodynamic system in a given equilibrium state has particular values for each thermodynamic properties. And those thermodynamic properties are called state function. All right, so a thermodynamic state function is specifically describing a thermodynamic state. Now, enthalpy itself is a state function, but the change of enthalpy is describing the difference between two different thermodynamic states, and hence this one is false. With me so far? Now, thinking about how to make this statement true, we can think like H itself will be a state function. So if we remove this delta here, and then this will become a true statement. Yes?
So are you saying that delta H is path?
It's not path dependent, but it is at the same time not a state function. So delta H describes the difference between two thermodynamic states. And that is why it is not a state function. So a thermodynamic state function describes a specific thermodynamic state, right? All right, next up. Yes?
Wait, so is delta U a state function?
No, it's the same logic, right? So internal energy U is a state function, but delta U describes the difference between your two different states, and hence it's not a state function. Next question. CV is independent of temperature for every ideal gas. So this one is not true, since we always specify, hey, ideal gas only tells us that we have CV equals to dQV over dt. And then this process, for ideal gases, my dQV equals to du. So my CV equals to du over dt. Now, ideal gas only tells me that my internal energy is only a function of temperature. Whether or not that function is a constant, that's uncertain, right? So we cannot directly make that statement. Next up, say delta U equals to Q plus W for every thermodynamic system at rest in the absence of external field. Read it carefully and see if you think it's true or false. So, in this question, we're missing one term to make it true, which is saying the system must be a closed system. All right. So pay attention to every statement in these true or false problems. In order to make, so this one is false, but if we add a closed system, and then that's true. That's our first law of thermodynamics. Next up, a process in which the final temperature equals the initial temperature must be an isothermal process. So this one is not true. And the way to think about it is you can think about a random picture. Let's say we're plotting temperature with respect to volume, right? So what this question tells me is that my initial and final temperature is the same. So that's my initial, and that's my final, right? So having delta T equals to 0 basically said we can take any path I like to go to my final state, from my initial state to final state. But an isothermal process is stating the temperature remain constant for all steps between my initial and final state. So that's my isothermal. So we have dt equals to 0. The other way to put it is for every isothermal processes, you have dt equals to 0, you have delta t equals to 0. But delta t equals to 0 doesn't tell us it is an isothermal processes. Okay, so that's why this one is false. Next up, for a closed system at rest in absence of external field, U equals to Q plus W. Again, something is missing here. What is missing? Anyone want to take a guess? Yes. Right, so it should be the change of internal energy equals to Q plus W. So this one is false, but if we add my delta here, and now we can make it a true statement. Next up, internal energy U will remain constant in every isothermal process in a closed system. So what do we think? So one hint here, thank you. One hint here is when I have internal energy for any complexes or any system, our internal energy is a function of volume and temperature. But for ideal gases, my internal energy is only a function of temperature. So that means this statement will be true if we specify it being an ideal gas. How does this pace feel for you? I mean, we're just going through every problems a little bit faster. Okay. Next up, G, we have Q equals to 0 for every cyclic processes. Yes?
I'm sorry, Professor, but back to the last one.
Mhm.
You said that it would be true, even though they didn't specify.
If we specify it being an ideal gas. So this one is false. But if we specify it being ideal gas, then it can be a true statement. So that's the whole point here, right? If we have a false statement, think about how to make it a true statement. All right. So G, Q equals to 0 for every cyclic process. So Q is a line integral, so obviously this is false. Next up, delta U equals to 0 for every cyclic process. What about this one? So this one is true, right? It's basically saying our internal energy is a state function. But instead of asking, is internal energy a state function? If I ask that question, most of you would be like, yes, of course, right? But if we ask it in a different way, then you want to think. This question is effectively asking, is my internal energy a state function? Next up. Delta T equals to 0 for every adiabatic process in a closed system. So we're talking about an adiabatic process in a closed system. So in this case, adiabatic process tells us our Q equals to 0. But we have no idea how does my internal energy change. We have no idea how does the work change. And naturally, we don't know how the temperature will change alongside with it. Next up, a thermodynamic process is specified by specifying the initial and final state of the system. So this is a difference between thermodynamic state and thermodynamic process. So in order to specify the thermodynamic process, we need to have an idea about what each infinitesimal step is. Right, so in this case, when we're talking about initial and final state being the same, only this isothermal path where dt equals to 0 is a specified thermodynamic process. Only specifying initial and final state is not sufficient to describe a thermodynamic process. Okay. Next up, if a closed system at rest in the absence of external field undergoes an adiabatic process that has W equals to 0, the system's temperature must remain constant. This one is a longer one, so let's just read it in what do we know by reading this problem. It tells us the closed system at rest in absence of external field, so we can use our first law of thermodynamics. So delta U equals to Q plus W. Undergoes an adiabatic process, so Q equals to 0, W equals to 0. So we have delta U equals to 0. But delta U equals to 0 doesn't necessarily tell us the temperature is constant. So this statement is false. And you see, like, by just reading it, you'll be like a little bit confusing what exactly that is. So just write down what those terms mean. Like this long description, closed system at rest in absence of external field, we can instantaneously write down our first law of thermodynamics, delta U equals to Q plus W. And then from there, do the subsequent derivation. Yes?
So if this problem specified that it was an ideal gas?
Yeah, then that would be true, because ideal gas internal energy is only dependent on temperature. See a question? Okay, same question. Good. All right, next up. PV work is usually negligible for solid and liquid. This one, I don't really like their statement, but this one is a true statement. The way to think about it is PV work is talking about expansion or compression of the system, right? So gas is pretty easy expanded or compressed by changing the pressure and volume. But say if I have a piece of chalk, which is a solid, I can apply pressure on it, but it's really hard to change its volume. So the PV work associated with that pressure and volume change is going to be very small for liquid and solid. But this question is less interesting one. Next one. If neither heat nor matter can enter or leave a system, that system must be isolated. So this one is another tricky one. Remember the definition of an isolated system is that the system doesn't interact with the surrounding in any way. Now, for example, in this question, we didn't specify the system doesn't have an external field, so potential energy can also play a role affecting the system's state. But I don't really like this question, though. It's a slightly tricky one. Next one. For a closed system with PV work only, a constant pressure process that has Q larger than 0 must have delta T larger than 0. So this question is a quite weird one, right? It only tells me heat is larger than 0. We don't know how work change, we don't know how internal energy change, and consequently, there is no idea we can conclude what delta T is. So we just don't have enough information to make a link between heat and delta T. Next one, a calculus problem. So for these kind of calculus problem, the best way to deal with it is to solve the calculus yourself and see if they fit, right? So in this case, we have it's between state 1 and state 2. We're doing the integral of 1 over v dv. Solving it, we're having log in v between state 1 and state 2. So that's log in v2 minus log in v1. Okay. Obviously, by our math and understanding of the logarithm, log in v2 minus log in v1 equals to log in v2 over v1, not v2 minus v1. So that's a false statement. All right. Next up, see the value of delta U is independent of the path used to go from state 1 to state 2. So this one is a true statement. Again, it's basically asking us whether or not internal energy is a state function. Next one. We have for any processes, the delta T equals to the delta small t, where the big T and small t are Kelvin and Celsius temperature. This one is pretty straightforward because my Kelvin temperature is just the Celsius temperature plus 273.15. But if we change this problem from like Celsius to Fahrenheit, then this is going to be a false statement. Again, don't try to write down everything because I will post my annotated note. Just really think about it before I tell you the answer, and then we'll go over the logic together. Next up, if Q equals to 0 for a process, then the process must be isothermal. So this one is false, right? So Q equals to 0 only tells us we have a adiabatic process. So if we replace that isothermal with adiabatic, then we have a true statement. Next up, for a reversible process, P must be constant. This is quite extraordinary because how come P constant is connected to reversibility in any way? So this one is just false. I don't even know how to make this a true statement. Nevertheless, next one is again a calculus problem. We have the same kind of calculus, and since we already solved it here, it's just not true, right? So this one is different from log in T2 over log in T1. Next one. If the final temperature equals the initial temperature, the process must be an isothermal process. So that's the example we did there, right? So having delta T equals to 0 doesn't define the path being an isothermal process. Okay, and the last one is again solving this calculus, integral calculus. So we have T1 to T2, T dt. If we solve it, we have 1/2 T squared between T1 to T2, and that ends up to be 1/2 T2 squared minus T1 squared, and that doesn't equal to 1/2 T2 minus T1 squared. So this one is false. All right, so this is a quick demonstration in like, well, what am I thinking when we're working, what should we be thinking when we're looking at the true and false problem? A few take-home messages. It's read the question carefully, and if the question is long, write out expression in thermodynamics that we learned in class, and then try to derive whether it's true or false. And when practicing true and false problems, try to give it a careful thought. I mean, if it is false, how can we make this statement true? If it's true, how can I take out conditions to make it a false statement? And I mean, we only spent like about 1 minute for each question. So that's the time you should expect, right? So how long you should spend on each true and false problems. All right, any questions here? Nope. Okay, sounds good. So next one. This one, I'll set up the problem with you, and then I'll do it on the board, so we can also work on this together. This problem here is trying to illustrate how can we go beyond the Carnot cycle that we defined. Remember, a Carnot cycle is by definition a reversible cycle, consists of 2 isothermal processes and 2 adiabatic processes. And now imagine we have a new cycle called Brayton cycle or Joule cycle. Now this cycle is used in heat engine for our, say, an airplane. Here's the setup. Let's assuming the Brayton cycle consists of ideal gases with constant heat capacities. And the setup looks like this. The system consists of my compressor and turbine that's filled with some kind of ideal gases. These 2 chambers are closed, right? So the gas will stay in there. The gas can absorb heat or give off heat, and also the gas can do work on the surrounding, or the surrounding can do work on that gas chamber. But the gas will not leave the chamber, right? That's a closed system. And in the middle, we have a combustor. So in that combustor, we will have fuel burning in the combustor, and the heat will transfer into the system. So how does that fuel burn? We don't care. But what we know is the heat can go in to the system, and the heat can go out from the system. Now, in the cycle, what we have, I already give you the picture, but for example, in the exam, we might, for example, just give you the adiabatic path and ask you to follow the pathways and finish up this PV diagram. But nevertheless, right now, I'm just giving you the PV diagram here. And what is happening? From point A to point B, we're saying this is a reversible adiabatic compression of the this part, the compressor, of the gas chamber in the compressor. So the system is doing work on the compressor to compress the volume of the gas inside the compressor. So from A to B, we see the volume is decreasing. And it's an adiabatic process, so it all comes from the surrounding doing work on the compressor. Next up, from B to C, we have isobaric heat input. So we call this one a Q2. So for both Q2, for this Q2, we're talking about the heat is being transferred into the system as Q2. From C to D, we have fuel combustion. After the fuel combustion, we have heat input into my system. So the gas will absorb heat. And then after absorption of the heat, it will do work on the surrounding. There are two parts of the work. The first part of the work will be used to restore the compressor to its original state. Let's call it work compressor. And part of the work will go out from the nozzle to do work on the surrounding. So that's our work output. And then from D to A, the last step is the cooling of the entire system because it's a cyclic process. We want to restore everything back to its initial state. So that's a cooling, and we have a Q1 associated with that process. We can ask a few questions, right? What is the whether like my work output is positive or negative, Q1, Q2, whether it's positive or negative, and my work compression, whether it's positive, negative, or zero. Like for example, in this case, since my system is my compressor plus my turbine, so my work compression is zero because it's the work within the system. Right, so whenever we're referring to these Q and W, we're always talking about how is my system interacting with the surrounding. But in this question, I'm just gonna, as a demonstration, to say like, let's calculate the efficiency of this Brayton cycle. And think about how do we set up this problem. All right, so in here, we know several things. And let's just think about how to set up this problem if you see it on the exam. There are different ways to solve it, but we'll always end up with the same result. The first thing, I like to set up by asking myself what the question is asking for. It's asking for the efficiency of the cyclic process. So we define efficiency to be work output over heat input. Right. So in this equation, we find out our work output or work output absolute over heat input. Now in this case, the heat is going into my system in my process between B to C, and then heat go out from my system to the surrounding between D to A. So Q2 is my heat input. All right, so now we have this equation. We want to think about how do we calculate W output and how do we calculate heat input. Because eventually, remember when we talk about efficiency, we can express that efficiency with temperatures on my PV diagram. So we can't have Q and W in my final expression of efficiency. We can only have temperature. So in here, how do we do this? Let's focus on this Q2 first. What do we know? What's the relationship between Q2 and temperature? So for this process, as stated in the PV diagram, it is an isobaric process. So for an isobaric process, what do we know? We have QP equals to delta H. Right, so we did this. So for the process between my Q2, which is the process between B to C, we're trying to calculate the delta H for my ideal gas going from B to C. And for ideal gases, we know something else. We know the delta H of my ideal gas equals to Cp dt. And the question gives us Cp is a constant, so my delta H from my process between B to C is effectively the same as Cp times Tc minus Tb. All right, so this is a link we're trying to emphasize. It's like how to use the things we know and use thermodynamics to solve for properties we want. And next up, now we have our Q2. What about our work? So for this process, how do we link work, heat, and something we know? We use our first law of thermodynamics. Remember, we have the system at rest, no external field, closed. So we are happy, we should be able to use our first law of thermodynamics. Delta U equals to Q plus W. And do we know what is delta U for the cyclic process? That's 0. So for the entire process, we're looking at our systems, the heat transfer into my system and the work done on the system. All right, so in here, what do we have? My Q total is effectively my Q1 plus Q2 because the other two are reversible adiabatic processes. So we have Q total equals to Q1 plus Q2, and that is the heat into system. Now, your heat, we say heat into system. Your Q1 and Q2 may or may not be positive or negative, but we're thinking about the process of heat flow into the system. And my work here, what we want is the work output. It's effectively the negative of the work in this equation, because we're talking about how much work is output by the system to the surrounding. And that gives us the final expression of Q1 plus Q2 minus work output equals to 0. So far, so good? And, well, we know what our Q2 is. That's a delta H between B to C. Likewise, we can calculate our Q1. That's the same as delta H between the process D to A. And that's our CP dt, or CP times TA minus TD. All right? And then we know what this expression gives us. My work output total equals to Q1 plus Q2 equals to CP times TA minus TD plus TC minus TB. That's our work total. And as a sanity check, for our Q1, remember we say this might be positive or negative. So my temperature at A is lower than my temperature at D. It's a PV diagram for ideal gas, so the product of PV is smaller at point A. So this must be a negative number. And it's physically making sense, right? So heat is like going out from my system to the surrounding in Q1, and it is a negative number. So it's a nice like sanity check. And now we're ready to calculate our efficiency. That's pretty much just this whole thing. So CP, TA minus TD plus TC minus TB over my Q2, CP times TC minus TB. My CP cancel out, we only have temperature left in my efficiency. All right, yes?
Could you explain why it's Q1 plus Q2 minus work out?
So this one, my work output, I want it to be a positive number in this equation. It's the work done by the system to the surrounding. But typically, in this original equation, both Q and W are referring to heat transfer into the system, work done on the system. So my work output equals to negative W here. All right, so in this original first law of thermodynamics, both my Q and W are referred to heat into system and work done on the system. All right, but in this setup, we know the work is output by the system, so that work output equals to negative W. So when we plug it in back to this equation, we have the Q1, Q2 minus the work output equals to 0. Yes?
Professor,
Professor said for Q total, the whole thing is heat into the system?
Yes.
But isn't Q1 heat out of the system?
Well, Q1 is the heat out of the system, but it's reflected by a negative number of Q1. All right, so don't add in that negative too early. Okay? So this is going to be a quick demonstration in what a comprehensive exam will look like. So for example, this can be one of the sections of a comprehensive exam. The other section might be, okay, so now we have this equation, calculate the efficiency given the temperatures of each point. Or at the beginning, instead of giving you the entire PV diagram, we can just give you descriptions on what's going on and ask you to plot these PV diagram on the plot, right? It's not super hard. For example, we have adiabatic compression. So you know that from A to B, the volume must go down, right? From B to C, that's isobaric, and heat input, so the pressure is the same, it's a straight line. Heat input, so your temperature goes up, the volume must go up, right? So knowing how to plot these PV diagram is important. Or alternatively, we can give you this PV diagram and ask you to say, can you describe the process of D to A, right? So that's an isobaric heat output. So these are the kind of questions might appear on a comprehensive exam. Now, have we seen Brayton cycle in our class? We didn't, but we have enough information to analyze the cycle that we never seen in class. All right. And if you want to read more about the Brayton cycle, just ask ChatGPT. And I know, right? Sometimes they give you wrong answer, but this one is a relatively good one on my end. Next one. Okay, we're back to our true and false marathon. So we have more true and false problems regarding our chapter 3 topic, which is related to entropy. Okay, back to the mode of true and false. So remember the steps we take for true and false. We read it carefully, try to identify what this question is asking about, and then answer it true or false. If it's false, we want to make it right. If it's true, we think about which part we can take it out, and then it becomes false. First question. A change of state from state 1 to state 2 produces a greater increase in entropy when carried out irreversibly than when done reversibly. Okay, so what exactly is this question asking? We are talking about delta S of a process between my state 1 and state 2. So the question is saying, if this delta S is happening irreversibly, it's going to be a different number than it happened reversibly. But we know entropy is a state function. So by saying it is a state function, we're saying as long as we specified its initial and final thermodynamic state, the delta S will always be the same. Right, so this one is false. And if you imagine the way we did is building reversible pathways leading to my initial and final state. The whole point we can do that is because entropy is a state function. So this is a very tricky question. It's very easy to get wrong. Next up, the heat Q for an irreversible change of state from state 1 and 2 might differ from the heat for the same change of state carried out reversibly. All right, so now instead of talking about delta S, we're talking about heat. So in here, heat is our line integral. So this statement is a true statement because for a line integral, then the path actually matters, whether it's reversible or irreversible. So this question, if we translate it into something you can understand, the first question is asking you, is entropy a state function? The second question is asking you, is heat a state function? And you know the answer to those questions, just how to translate the long statement into that simple question. Next up, the higher the absolute temperature of a system, the smaller the increase in its entropy produced by a given positive amount of dq reversible of a reversible heat flow. So it's asking about, well, entropy, dq reversible, and temperature. Let's just write down the definition of entropy, right? So my ds equals to dq reversible over temperature. So naturally, if my dq reversible is a constant positive number, then at higher temperature, my ds will be smaller. So this question is correct. Okay. Next up, the entropy of 20 grams of liquid water at 300 Kelvin and 1 bar is twice the entropy of 10 grams of liquid water at 300 Kelvin and 1 bar. So in this question, what it is asking, for example, by specify 300 Kelvin and 1 bar, we're specifying that both of my liquid water are in the same thermodynamic state. And then the difference between the two 20 gram and the 10 gram, just a number of more. So effectively, this question is asking us, is my entropy an extensive or intensive property? So because my entropy is an extensive property, this statement is true, right? So double the amount, double the entropy. The next statement is related. So question E, we have the molar entropy of these two 20 gram of liquid water or 10 gram of liquid water will be equal. So in this case, it's asking, is my molar entropy an extensive or intensive property? So by writing out my molar entropy, which is entropy with a subscription m, that equals to S divided by N. So that is an intensive property, and hence this will be true statement. But you can easily make them false, right? So by switching, like this one is the same, this one is twice, and then it's easily switched. So do read it carefully. Next one. For a reversible isothermal process in a closed system, delta S must be 0. A reversible isothermal process of a closed system. So what do we know about reversible isothermal process? So for a reversible isothermal process, we have ds equals to, well, the delta S equals to the integral of dq reversible over temperature. And for isothermal processes, we can simplify this expression as dq reversible over temperature. Right, so now the question becomes, is heat always 0 for isothermal processes? And the answer is no. All right. Next up, the integral given is always equal to CV times ln T2 over T1. So again, for this kind of math problem, we just solve our math. So we write it out as from 1 to 2, CV over T Now, do we know how to solve it? Because CV might be a function of temperature. So we don't know how to solve it. This is only true if we give you that CB is a constant. Next up, we have the system's entropy change for an adiabatic process in a closed system must be 0. So this one is again a tricky one. The system's entropy change, so we're talking about delta S. So writing out delta S equals to the integral of dq reversible over T. It gives us adiabatic process. So we have the total heat transfer equals to 0. But we don't know whether or not the process is reversible or not. So the dq reversible is not necessarily 0. And hence, this is a false statement. We can make it a true statement by specifying it being a reversible adiabatic process. Next up, thermodynamics cannot calculate delta S for an irreversible processes. I hope you all know this is not true because we spent our entire lecture talking about how to calculate delta S for irreversible processes. And again, because entropy is a state function, that's why we can build reversible paths. For a reversible process in a closed system, dq equals to TdS. So again, go back to our original definition of ds, writing this like 5 times already. So this equals to dq reversible times T. So since we specified it being a reversible process, that is a true statement. And the last question. The formula of section 3.4, which is the whole derivation we did last Friday and this Monday, enables us to calculate delta S for various processes, but do not enable us to find the value of S of a thermodynamic state. So this one is a true statement, right? So for everything we're doing, we're always talking about delta S equals to the integral of dq reversible over T. We don't know what we're referring to because we haven't give zero entropy a definition. We'll do that in our third law of thermodynamics. In there, we'll give zero entropy a firm definition, and then we'll be able to talk about absolute entropy. Okay. I hope today is a nice review on some of the things we covered. Again, we spent lots of time talking about true and false, but these true and false can be easily translated into like a short answer problem, asking for your explanation. And this is a good demonstration in what a comprehensive exam might look like. All right, good luck. I'll see you on Friday. Your TA will be with you tomorrow for tutorial session.